Hello, everyone, and welcome to the Material Minds podcast, place where we talk to the people exploring new materials for a better world. Today, we have Yale's Vreeken, professor at CISPA, the Helmholtz Institute for Information Security, where he heads the group of exploratory data analysis. Now, he took me on a journey of his vision to create artificial intelligence systems that can gain real-world understanding through analysis of data and thereby propel scientific discoveries. It's a field that's very new to me, and he does an incredible job with anecdotes and stories and explanations for the science, which just blew my mind. And I'm sure you're going to enjoy this episode a lot. Let's go ahead. Hi, Yillis.
Hi.
Welcome to Material Minds, and thanks for joining us.
Thank you very much for having me.
Yeah, absolutely.
It's my first time in this building.
Yeah.
And I'm also first time on a proper podcast. So
that's wonderful to hear. Yeah. Wonderful to hear that we're a proper podcast. But yeah, so we'd like to get to know you first. And as usual, we'd like to get to know you through the game of 3 truths and a lie. Yes. And I hear that you've prepared some of these statements for us. So you're going to tell me 4 statements, and 3 of them are going to be the truth. 1 is going to be a lie, and I've got to figure out which one that is. I'm going to dig into it a little bit. You can very easily fool me in principle, but let's see. Yeah. Let's see if I figure it out.
Okay. Well, no, that's so indeed I prepared a little bit, it's a bit more difficult because most of your guests here are material scientists, right? And talk really about material science. And then given that you're a material scientist, you can read, of course, I'm a machine learning and a computer scientist. So that may make it a bit more difficult. So I figured, you know what, the first fact is not so much about my research, but more, let's say, my research life. That's the first, I would say fact for you to discover if it's a true fact or an alternate fact. So I finished my PhD in 2009. In the Netherlands, Utrecht. And afterwards I started a postdoc in Antwerp, in Belgium. And I was with the goal to become a professor. I want to become a professor, or so I thought. And then a year into my postdoc, I got a phone call. And the person on the other line was a professor I knew. Like, okay, well, we have this really cool project and we're looking for a professor. This is going to be an assistant professorship, 10-year track to associate professorship. And as long as you don't completely screw up, it's going to be a permanent position.
Nice.
That's nice. Yeah. I turned it down.
Okay.
That's the fact.
You turned it down.
Yes. A year after my PhD.
You got this amazing once-in-a-lifetime sort of opportunity that everyone dreams of, and you turned it down.
I'll make it even stronger. I'm from the Netherlands, like I already said. I was born in Amsterdam, and it was always my dream to become a professor at the University of Amsterdam.
Okay. Was the offer from there?
There was a consortium that included. Yeah.
Okay. All right. Can you give me any details about why you turned it down?
Yeah. So I think the real reason is that I'm a little bit crazy. I'm perhaps not clinically insane. I don't have the diagnosis as such. Right? So, you got the recommendation to invite me from PTSD in action. So maybe that is the reason. Like, whoa, this is going to be interesting. But that is one of the reasons I think that I am just simply a bit insane. But I also have a reason. Well, at the time, at least in my head, was quite rational. And this was essentially then going to be a professorship in a field that they then called e-science. Have you ever heard of e-science?
No, not really.
Neither had I.
Okay.
E-science is the science of basically using computer science for science. So effectively, right now we would call machine learning for science or AI for science.
Yeah, sounds like it.
And I didn't feel it.
Okay.
I didn't feel it. It's like, okay, this is not what I want to do.
Okay. What were you doing at the time?
I won before I started my PhD. I'll walk you through it. I was very interested in AI, and particularly intelligence. How does intelligence work? Was really what was one of the
like
key questions.
regular human intelligence.
Yeah, natural intelligence. So how do our brains work, right? And not, how can we go about our day without stumbling into things all the time? Some people are more clumsy than others, right? But generally, we can survive reasonably well. And how does this work? And so I started studying computer science with a focus on AI. I rolled into the field of robotics. I learned that robots are highly suicidal. So basically, if you train a robot to stay on the table, the first chance that it gets when you look away, it will stumble off the table, it will break into 1,000 parts, and you have to reassemble it.
Yeah.
I've done that many times. Okay. Studies. So at one moment I realized, okay, no, that this is not, in the next 20, 30 years, robotics is not going to go anywhere. Okay, so another token of my sanity, right? And then from there, I decided, okay, well, this is not where I wanted to go with my PhD. And then I stumbled, after a few lefts and rights, into first bioinformatics and then later a field called data mining. And data mining, the idea is to, develop algorithms, methods, right, that can rummage around in data and essentially tell you what was going on in the data. And this you can use for anything. So you could even use it for science. But you can also use it for business optimization or whatnot.
And that's what I used.
This is what I studied during my PhD, and to a certain extent what I still do.
Yeah, that's true. And so then in your postdoc, did you switch gears when you had this opportunity come up?
No,
it was the same direction?
I got a phone call. I thought about it. Well, it was not in 5 seconds. I had this it took perhaps 5 days, but then I said no, and I basically carried on what I was doing.
Okay. Interesting. Okay. Well, I know that you're not in Amsterdam, so that
is true.
Maybe helps, but there could have been switches in the middle. Maybe one last question on this. Do you regret the decision by any chance? I know you're in a great position right now, but no. Okay. Not at all.
Regrets are useless.
Okay. So, yeah. Okay. Then... I think that's as much as I'll dig into that one. Then let's hear your second factoid.
So we're going to switch gears. So a very large part of my research is based on information theory. And information theory is essentially the very fruitful marriage between statistics on one hand and mathematics on the other. Bit of physics. It's a Shannon information theory, you could say, is inspired by Boltzmann entropy. But then formalized towards information. And this is a beautiful theory. Good theories are beautiful just mathematically, right? And that just when you look at them and you can make all sorts of inferences.
Yeah.
But information theory is not just beautiful on paper. You can actually make it work. So the original proposal of information theory is how can you transfer as much information over the airwaves, right? Stuff like this. But the idea that we've been exploring during my PhD and afterwards is how can we take a data set and then look for the best possible compression of this data set. But as information theoretically, the optimal compression. And that allows us to, if you have a data set, material science data set, right, or anything where you want to predict a certain property or you want to gain certain insights, that allows us to develop a method that can tell if the data that you have, if it actually contains the information that you need for the task that you want to solve, or whether it's like, you can pray to the gods of data science as much as you want, right? But from this data, you will never be able to reach your conclusion. And the other way around, that if our magic 8 ball says yes, and you can't get it, your machine learning method to work, joke's on you, because it is possible. Okay. You just have to wag your finger more sternly at your deep neural network. So basically we can tell, is the answer in your data yes or no?
Okay.
Like magic.
And is this based off of statistics in any sense?
Yes.
Yeah? Okay. Yeah. Probabilities and statistics.
Exactly.
Yeah? Okay.
So the very general idea is that the higher the probability of a certain phenomenon occurring in your data, right? If you want to compress your data maximally, then you should assign a very short code, short, like a code word of very few bits to that particular phenomenon.
Okay.
And things that are very rare, you don't need a short code word. Actually, that would be harmful because you can only use so many short code words. At one moment, you run out of short code words. You best assign them to the things that are most prevalent.
Yeah, okay.
That is exactly what we're exploiting here. So if
Okay.
you can find exactly the right assignment of short code words
Yeah.
to highly prevalent phenomena,
Yeah.
then, well, you are at the essence of this.
Yeah, okay. But what you're saying is, or the way I understand it, is that it's some data set. Do you need to know what the data set pertains to? Like, does it have material science, or you need? No, okay.
Information theory is about information.
It's difficult for me to wrap my head around this, for sure. It does sound like magic, but so does a lot of the artificial intelligence stuff that we have going on now. Yeah, exactly. Does this have any relation to the way like large language models or diffusion models sort of work in, we put a query and then it finds from this huge space of whatever what makes sense and brings it together?
Yes, in the way, well, not exactly with the query, right? But effectively, if you think about what is a large language model, right? Large language model, I mean, if you look at ChatGPT and friends, right? I mean, it's almost like magic what they do, but they're incredibly stupid. If you look like how they function, right?
Yeah.
And effectively, a large language model is a model that predicts the next word given a window of the previous words, right? And this is also literally what you see if you play with these bit with Claude, for example. See these words popping up one at a time. This is not some quirky user interface. This is literally how they generate. They generate word after word, and in this process, there is a bit of randomness, right? So they don't always generate exactly the same word.
Yeah.
Because if you do that, then you get very boring sentences that nobody finds interesting. And that steers them, well, then in the end, if you give them a prompt, they just start generating the first word that is what somehow they think the most likely given this prompt. And then the second word they generate is the word that is most likely given the prompt plus the first word. And so on and so forth. There is no like mental processes or so. Right?
Yeah.
Now, that is how they work if we like ask them a question. Now, if you think about it, the most likely word is effectively that word that we would give the shortest code.
This is what I was thinking, yeah.
Exactly. And if you now start to think about how is a large language model actually being trained, right? How does this work behind the scenes? We have a large piece of text, right? I mean, so OpenAI and Anthropic and whatnot may basically discourage the entire internet, right? I mean, that's... but effectively what they do is that they ask the large language model, what is the first word of, well, let's say this article of Wikipedia? Of course, there's no clue, right?
Yeah.
So it will just say randomly, well, it will choose a word that is likely.
Yeah.
The word "the" is very likely in the English language, right? Just like and whatever, I mean, laser sword like lamp, right?
Yeah.
I mean, is a bit less likely, but it could be the first word in Wikipedia for all we know.
True.
Now, effectively, it now chooses the word a bit randomly that it thinks is most likely, but it could be "the." And then, well, it gets a penalty for the, let's say, the mismatch between the word that it predicted and what it should have predicted. And the further off it is in this likelihood, right? So in how likely this word is, if it predicted like laser-like sword, I said, then like, okay, dude, what is this, right?
Yeah.
And then gets a large penalty. And if it gets the word right, it doesn't get it gets a reward or it doesn't get a penalty, right?
Yeah.
We're very stern in machine learning, so it's always penalties. There's no rewards, effectively. And now for the next word, is again, it now needs to predict what is the most likely word, given, well, it has already "the." So it is probably going to say a word that logically, like grammatically correctly, will follow the word "the." And that could all of a sudden be, well, laser-like sword, whatever, right? I mean, that's, but the horse is probably a bit more likely, so it will predict this. Now, effectively what we're doing, right, and is that we're now looking at which word is there actually, and what is the probability that the language model assigns to it. And the more these are aligned, the better, right? And the more these are aligned, the better it is compressing the data. So a large language model, by just going over all the words and time and again sort of like pushing it a little bit like, no, no, it's horse, no, it's this. Then after a while, it gets all these probabilities right within the right context, and it allows it to continue the sentences as it's supposed to with very little penalty. And this penalty is exactly the number of bits that we have to pay in addition to what it's saying. And of course, the fewer bits we have to pay in addition, well, the better it is. So a large language model, in that sense, is also compressing the data. And that is why I think large language models are so good at what they're doing because they're compressing. It's in the anti-information theory.
Yeah, okay. Okay, so there is a connection, which means even if what you're saying is like magic, it's sort of believable magic because, we use it all the time now.
Exactly. But as you know,
that's a tough one. Yeah.
As you say, I mean, all the best lies are rooted in truth, right? So,
that's true. Okay, then I got to hear your next one, and
okay, so I'm now gonna ramp it up even more because what I would say is that the goal of machine learning, goal of science, also physics, is discovering laws of nature. How does the world work? Right?
Sure.
And what you're saying about consciousness is definitely not far off because in order to operate in the real world, we also need to know how the world works.
Yeah,
right? True. And it's not just associations. Not just associations, right? For example, right, if you would be an AI, right, and that, or you have the role to determine for somebody who's very sick, right, and that should we bring them to the hospital, or should we leave them or bring them to the shopping street? Which of the two?
Yeah. Bring them to the hospital.
Bring them to the hospital.
Yeah.
Well, that is, of course, a horrible choice because in the hospital, people die all the time. But in the shopping street, I mean, I don't know when the last time you were there, they seem to be quite happy they're alive, right? So no, we should not bring them to the hospital. Okay, so if you think about it purely statistically, then what I just said is not insane. This is actually correct. Right?
Yeah.
However, if you think about how the world works, then then it's good that you're the AI.
Yeah.
Not me, right? So what it's about is that you need AI that understands causality. It understands how the world works, understands what is cause and effect. And if somebody is sick, well, then the sickness needs to be fixed somehow, right? And that, they do at a hospital and not in the shopping street.
Yeah.
Right? And why do people die in a hospital? Yeah, because very sick people out there, and very elderly people, right, who have a tendency then to die more than young people or rushing around in the shopping street. If you feel terminally ill, you don't go shopping. All these things. This is common knowledge in a way, but it's common knowledge about how the world works, about causality. Same thing for material science. You're trying to understand the physics of materials, right? And also like predicting a certain property of a material. Well, sure, I can say that. Okay, I'm actually not going to come up with a random example that I didn't prepare, but I'm still trying to. But I should. Still, perhaps a good example comes up.
Like rock is hard.
Yeah, it was something like this. Yes. So, one of my favorite examples is that, for example, the laser pointer or laser in general. I mean, so the discovery of the blue laser, that resulted in a Nobel Prize for this Japanese research, if I recall correctly, because for a long time, like, okay, how the hell do we get a blue laser? We had red, we had green, right? But the blue one, how do we do this? And the discovery of this was complete happenstance. Just rolled into it. He observed some weird anomaly, right? And then focused. This was... Now, had we not used human ingenuity and like, hey, this is strange, then rather, I mean, it doesn't exist because this material doesn't do it, this one does. So statistically, no. But why did this researcher now scratch his head in what the hell? He observed something that didn't fit their word model, of their understanding of the world. Right? Same thing with discovery of penicillin. This is also completely like, okay, so why am I bacteria dead, right?
Yeah.
I mean, who did this? True. Right? I wasn't in the room, but this is how I am kind of imagine that it didn't fit the world model, and that set people to think, hey, wait a second, then this was different, so this must have caused that. That is where we need to go with AI. Now, me and my group, we're working on causality, and we've developed now methods that can, if you give me a data set, it can tell you what is the cause, what is the effect.
Okay.
Just from the data alone.
Just numbers again.
Just numbers.
Okay.
You just give me the numbers. We don't care about what it is. Right? Just numbers.
Yeah.
It could be also colors and whatnot.
Yeah.
Okay. Categorical features, right? And we can tell you, okay, this is the ground truth. This is causality.
So this is all sort of like statistics on steroids.
Yes.
Quite a bit. Okay. Because we struggle with these kind of things, right? In our research,
But we solved it.
That's your statement.
That's my statement. Yeah, that's my statement. Yeah.
All right. Okay, I'm going to think about this, but let's hear the fourth statement, and then we'll see. We can recap it. I'll try to figure it out.
Yeah. Okay, fourth one. So since, I don't know, last give or take 10 years or so, right? Biggest craze in ML and in AI is deep learning, deep neural networks. So everybody's using deep neural networks, and well, many people have a bit of a love-hate relationship with them. That's because you can get them to work like remarkably well, but they also, as my PhD advisor called it, they're highly neurotic. So they also like the next day, like they don't do anything anymore, and you have to poke them with a stick.
Yeah.
But the biggest gripe that most people issue about deep neural networks is that we don't know what they do. They don't know what they do.
Yeah.
And well, first of all, in general, okay, I can challenge this because we can write them down mathematically. We call them neural networks. Basically, it's just a stack of functions.
Yeah.
I mean, mathematically, it's just easy, right? This is a trivial statement.
Okay.
The truth or the lie. Now, a very big stack of functions is still maybe very difficult to interpret, right? To determine, okay, why is it saying this and not that? Now, what we developed a method that can explain how a neural network comes to a conclusion, how it processes from, if you give it like, okay, a picture of, let's say, a cat, right?
Yeah.
And that's, why does it say cat? So how, like, which features does it pick up on, right?
Yeah.
In which layers, which groups of neurons? Now,
Yeah,
these
okay.
neurons, they detect, let's say, pointy cat ears, right? And that's these groups of neurons are more like the whiskers.
Yeah.
These pick up eyes. And then later on in the network, this gets assembled into, okay, well, if you have whiskers and pointy ears, well, it could still be a mouse, right? But if it then, well, has these, then it's a cat, otherwise it's a mouse.
Yeah.
So we developed a method already now 5 years ago
Okay.
that can pick up which groups of neurons encode what concepts, these flows of the network through the like how information flows, how it's processed.
Yeah.
And above all, and this is one of this is where then sort of things become perhaps tricky for you. One of the main focal points in machine learning right now is how can we explain these neural networks? We've already done it. How on earth can we figure out superpositions? Well, this is a connection to physics, of course, right? Neural networks also exhibit superpositions in the sense that different neurons, right, or a single neuron can actually encode multiple concepts at the same time.
Okay.
Depending on how active or not active it is. They do this in groups. So if this one is very active and this one is not so active and this one is so active, then it's cat. If they're all medium active, then it's dog, and so on and so forth. So this makes it very difficult to really pinpoint how, but we already solved this.
Okay.
So our method from 2020, 2021, in that time frame, has already solved interpretability of neural networks.
Okay.
And, well, people are only slowly rediscovering this.
I've heard this word explainability thrown around. Is this
this is
a bit of what
exactly.
is along these lines?
Exactly, yes.
And do you figure this out based on like the weights in these neurons? This is pretty much the only word I know in
No, so it's actually it's we could have. It's a very good, but it's even simpler. It's even simpler. I mean, this is why our idea is so good. But effectively, what we do is the following. Somebody gives us a deep neural network that they would like to gain some insight in. Right? Let's take, for the sake of the argument, a network that can detect cats, dogs, fire trucks, whatever. Right? I mean, that's podcast microphones. That's just a throw in a fourth concept. And what we now do is this network, they trained it and they're happy with it, gets an error of 0.42, right? And and they also give us, or otherwise we collect it ourselves, a number of examples that we feed one by one to the neural network. And then what we do is that we see for all of the neurons in the network, how active are they? So in the first layer, this one is very active, this is not so active, this is active, not so active, and so on and so forth, right? So we do this for all the examples. We have a giant matrix. Right?
Okay.
So where each column corresponds to a neuron, every row corresponds to, in this case, a picture that we gave the network. Right? And what we now do, we binarize this matrix. We round it.
Okay.
So for the neurons that are not active, we set them to 0.
Okay.
And the ones that are active or active enough, we set them to 1.
Okay.
Right?
And then you just see...
And then we have zeros and ones.
Okay, yeah.
And now we can apply pretty basic statistics.
Okay.
Then we can count. And counting is something I'm pretty decent at. I mean, computers even better at. How often do we see this neuron to be on when the other is also on?
Okay.
And if neurons A and B are very often on together, well, that is somewhat surprising, right?
Yeah, makes sense.
And that we can, if we now start from the prediction that networks, so when it says cat, right, then okay, well, when it says cat, which are those neurons right before that tend to be active when cat is active?
Yeah, okay.
And then for those, we can again see which neurons are now active right before that, such that, and then we can just trace all the information through the network.
Okay. And does this, the practical application of this, is this to say, can you figure out if your neural network is reliable for a certain task that you give it? Right? Like now you said cat and mouse and whatnot, but let's say the same concept is being used for studying MRI scans or something, right?
Yeah.
So then you'd be able to say that, okay, this neural network makes sense, sort of.
Absolutely.
Or you can explain what's happening in there at least.
Exactly. And twofold is an excellent question. So even twofold.
Okay.
So each for an MRI setup or for basically anything where you have like some visual input, for the example that I gave, right? And I need to predict something. For example, MRI, let's say a chest scan and it's tumors or whatever, right? I mean, let's say a tissue that somehow is doing something strange, right?
Yeah.
That somewhere in the network this needs to be encoded.
Yeah.
What we can now do, the moment that we found such a group of these neurons, there's other techniques we didn't develop. We don't solve all the world's problems. Right?
Yeah.
I mean, that's with causality and information theory and this, we already solve enough.
Yeah.
If it's,
At least 3 of them.
At least, yeah. So, yeah. You only asked me to make 4 statements, right?
True.
Otherwise, it would have gone on and on. Now, for such a group of neurons, we can now try to figure out what would be the ideal input, what would like the network really like to see, right? Or if it sees this, then these neurons are on. And that allows us to then, look at this picture and, identify like where in the image is it looking, what would it like to see in order for, so that allows us, for example, with the cat, if we then we get sort of whiskery pictures. Okay, this is whiskers.
Yeah.
And these are eyes. In an MRI, they say, hey, wait a second, these are ribs, right?
Yeah.
And this is, okay, this is some weird mass, and so on and so forth. But we can trace back both where the network is looking, as well as what is it looking for.
Yeah, okay.
So that is the one thing. That is really where this is useful, right? Because we gain some understanding that it's not triggering on, because that was a very, neural networks are extremely lazy. And they happen to love taking shortcuts, as we call it. So rather than learning the real concept, they'll just learn something spurious, right?
Yeah.
But, so, for example, in sticking with chest scans, in the early days of COVID, right, and that so when we didn't have all the nose tests and more tests, whatever, right? I mean, these types of things, people were relying on chest scans. And it was like, oh my God, machine learning to the rescue.
Yeah.
So lots of researchers, they started to train deep neural networks to determine for a chest scan, is this a COVID patient, yes or no? Now, for this, you need training data. And, there were some examples of people with COVID, right? Maybe not so many. But you also need, of course, then chest scans of people do not have COVID.
Yeah.
So what people did, they sort of dug in the archives and found some chest X-ray scans from before COVID, right? And used those. And they got neural networks that got like a 99.9% accuracy. Amazing. It was amazing, right? That, and then they tried this now on in the wild, and all of a sudden performance really went to 0.
Okay.
Wait a second, that is a very big discrepancy. What is going on here? Then they dug into, didn't have our techniques yet, right? So they didn't use them. What turned out, they were actually training this network on adults with COVID, typically very late stage, right? So like really bad, and X-rays of children.
Oh, okay.
So you guess what the network now learns to differentiate, right? I mean, it is a kid or not.
Yeah.
And
okay.
That is not so.
So okay.
In other cases where they got rid of the children MRIs, but they got chest X-ray scans done from adults, and it still got like a 99% accuracy, or 99.8 perhaps.
Okay.
In training and in practice, again, maybe 5%, maybe a little bit better.
Okay.
What it learned to do is that for the chest X-ray scans of like really like serious patients, right? I mean, they had on the X-ray in the bottom right corner some markings. And you see where the story. It is really important to be able to tell where is this network looking.
Yeah.
Otherwise, we can't trust it. Right.
Yeah.
So on training, sure, you get brilliant numbers. But then it doesn't generalize.
Yeah. Okay.
So this is where this then is super useful.
Yeah. Okay. That now the ball's in my court.
Exactly,
It's a tough one to take. The 4 statements that you had. First one, you passed up on a dream opportunity, right? The second one is that you can identify if a phenomenon is present in a data set that you're looking for. Third one is cause and effect. Whether you have in this, maybe I wanted to ask, is this like you have two data sets and you determine if there's a cause and effect, or is it one big data set?
One big data set.
And then there's cause and effect within there.
Exactly. Yeah.
Okay. And the fourth one is what's stuck in my head still as explainability.
Yes.
Or interpretability.
Exactly.
And so on. Yeah.
We can explain what is going on in the neural network.
Okay. Yeah. Let me think. I've really got I'm going to go with your statement 3 on cause and effect. I feel somehow there's something in my neural network that kind of tells me that cause and effect would be the most difficult thing to pull out compared to the other statements that you made. The first one, the fact that you're in CISPA now kind of pulls me away. Like, it makes me believe that you and that you are a little bit insane is something I could believe, considering all the other statements you said afterwards. So I will go with statement 3 on cause and effect.
Correct.
Correct?
Correct. Yeah. Correct.
I was nerve-wracking.
Correct. But as I already said earlier, I mean, the best lies are rooted in truth. So we actually have methods that can almost do what I claim.
Okay.
So now the tricky part is, it is impossible to derive cause and effect, right? Or really causal claims from data alone.
Yeah.
This is just simply mathematically impossible. Right? And this is where you don't know this because you don't work exactly in my field, right? But it is really mathematically impossible.
Okay.
So anybody who ever says, okay, well, I can really tell what is caused just from data alone, right? Because I trained my deep neural network and predict cause and effect super well.
Yeah.
Don't believe them, right? I mean, so it will be one of those COVID examples, like it will do something different.
Yeah.
Associations tell a lot about causation, right? I mean, so correlations do not imply causation.
Yeah, exactly.
But causation does imply
correlation.
Yeah. So there is smoke, and just where's the fire, right?
Exactly.
Now, so causality you can only determine from data if you're willing to make assumptions. About how the world works.
Yeah.
For example, that's the system was perturbed so and so, right?
Yeah.
Or there are certain noises involved, or we have measured everything that is relevant. Let's stick with that one.
Yeah.
Suppose we go for we have data about ice cream sales and shark attacks.
Okay.
Right. I mean, that's a standard example.
Yeah.
And we over the years, right? I mean, we dive into the archives and we take note of this, right? I mean, that's you will find a remarkable statistical association between the two, right?
Yeah.
And that's okay. Well, now you could say, well, suppose that we are now an ice cream company, right?
Yeah.
We started an ice cream company after this, right? And I say, okay, well, we want to drive up ice cream sales. What we could do is we could get some VC money, buy a lot of sharks, right? Dump them into the ocean, right? And then, well, no, right?
Okay, I guess
It could be the other way around. We could be politicians that are very concerned, right, in our coastal region about, our voters eating their sharks, right?
Yeah.
So we want to ban ice cream, right?
Yeah.
No, right? So, no. Of course, what is now very important here is the assumption, are we considering all relevant factors?
Yeah.
And in this example, might there be a third factor that actually explains everything away?
Yeah.
When do people... When do they go swimming out in the ocean? When it's sunny weather, right? I mean, that's now, like today, no, right? There's going to be very few shark attacks. At least in this part of the world, right? That when do people typically eat ice cream? Same. I mean, right? So there is a hidden confounder here. So there's a confounding factor, namely sunny weather, and it's hidden because it's not in the data.
Yeah.
And if you don't have it, you can't make any definite statement.
Yeah. And I think this is what drove my intuition towards the direction, because we face this all the time in experimentation, right? Yeah. Like we have to have like 10 different controls for one experiment because, especially in biology, where we want to make sure that none of the other factors are playing a role here.
Exactly.
And this is, I think, what triggered me a little bit when you said that it's just a pure data set, it's pure numbers.
Yeah.
it just didn't compute, I guess. But
however, that's so the best lies are rooted in truth. So because we can kind of do this,
okay,
right? But we need a little bit more than data. We need some assumptions about how the world works, and then under those assumptions, if they hold, we can actually derive causality.
Okay.
So, for example, in the biological example, right, that we spoke about, there, if you have recorded a certain organism in this case, right, under different circumstances, right, where different genes have been knocked out, or been, let's say, different. Let's say if you look at bacteria, I mean, different types of food or circumstances, right? And you can then observe how do they behave, right? How to sequence them, or you look at protein activations and stuff like this. Then if we are willing to make an assumption that causal mechanisms are relatively stable, right? So they don't change all the time, because that would be kind of weird, right?
Yeah.
And that if there's a change that happens to be relatively independent, let's not go into the mathematical details.
Yeah, okay.
But it allows us to discover strong invariance, as well as, well, if I say weak invariance, that sounds then pretty bad, but invariance that hold most of the time, but not necessarily all of the time.
Yeah, okay.
And then all of a sudden, if you give me data of this bacteria or something else, in the different circumstances, we can actually pick up the basic building blocks.
Okay.
And if we are willing to believe that causality is relatively stable, which, well, in our understanding of the world, it is. Right? I mean, not so. If right now, I mean, gravity would also invert. But it would rock my world quite literally, and yours too, probably, right? So certain things are relatively stable.
Okay. So ground truths, and this gives you sort of the context of reality that you're working around.
Yes, exactly.
And based on that, you can then pull out these things, which is incredibly powerful in itself.
Exactly. Yeah.
Right? Like, I mean, it's not as good as what you said in your lie, if pure data and whatever, but it's much more sensible and incredibly powerful.
Exactly. Yeah.
So maybe coming to the point of this being a material science podcast, is this have these things that you're developing and you've developed been applied in material science?
Yes. So the examples I just gave, only one of them has been directly applied, and that's also why I chose it. That was the one about using information theory to tell, is my data, I mean, does it contain what it's supposed to? So this is a collaboration that we had with scientists from the Leibniz-Institut in Berlin, the theory group of Matthias Scheffler back in the day. And they were very interested in using machine learning, or seeing like what is the power of machine learning to, well, discover laws of nature or laws of materials, right? Also towards discovering and optimizing new materials, very similar to what INM's mission is. And there, one of the interesting tasks that we started on working together, they had already been looking into, were so-called octet binaries. So combinations of certain groups of atoms. And in total, I mean, there exist, at the top of my head, was it 81 or 82 combinations? I forgot exactly.
Yeah, okay.
And it's simply, that's the number, right? That's the number of samples you have in your data set, right? And for these materials, we can predict, or we can compute all sorts of features, right? I mean, hundreds of thousands easily. But we have 82 data points. Yeah, that's it.
Okay.
And what they would like to determine back in the day, how can we predict now the crystallization structure? Is it going to be a rock salt? Is it going to be a zinc blend? Or is this something that, well, it depends on the hour of the day or something like this? And there existed some theories, but they were predictable, but they were convoluted. They didn't really make sense. So they had developed a method themselves and did a bit better, but it was not like completely crystal clear yet. And the question was, okay, can we do better? We don't know how, right? Okay, well, before we apply any fancy methods, let's actually see. So this is where we then we figured out that at one moment we're looking at a set of features by which it would not be possible to predict any better. And then, well, we enrich the features by taking, let's say, logarithmic transforms or whatnot, right? I mean, or combining. You can imagine, right? By measuring some additional things. That's just simple. Until that meant, right now it's possible. Well, their methods that we tried, the simple ones, did not necessarily do better. So then we scratched our head. So it should be possible. And then there is a topic that we didn't get to discuss, but which we explored quite a lot with them, is the topic of subgroup discovery. There's a branch of machine learning and data mining. It's not very well known, which surprises me because I think it's one of the most fundamental methods that scientists need.
Okay.
Well, I mean, I guess that just intuitively you know what a subgroup is.
But
you have some data, and there is something. You can also call this a subpopulation. And in theory, you could identify any group of data points as a subgroup, right? Of materials, or if you have census data, right? Just an arbitrarily group of people. However, a good subgroup has a description. And the description would be, well, let's say all all materials that are planar, right, in this database, right? So you have planar and non-planar ones. So we grab part of the data, right, and it could be, let's say, all planar molecules with between 3 to 10 atoms.
Yeah,
I don't know, or with 2 dual bonds, something like so. But as you can imagine, that shrinks the subgroup, right?
Yeah.
And now we are specifically interested in such subgroups that behave somehow special on a certain quantity of interest. Let's say the van der Waals energy, or the crystallization structure. In this particular case, it was okay. Under which conditions do we now really have a group that is going to be primarily zinc blende, primarily rock salt, or whatever, right? Behaves differently than the overall population.
Yeah.
And then it actually turned out that on this enriched feature set, if we used relatively standard methods from subgroup discovery, which essentially searches for these, you can think of it as selection queries on your data.
Yeah.
Right? Combinations of properties, you get select a part of your data, you look at the distribution of the target, and you see, is this different than the rest of the data? And if so, okay, we report it.
Yeah,
and then you just, your method carries on.
Yeah.
So it's a bit related to predicting, but in prediction, you're only interested in, the model that predicts overall best.
Yeah.
And this is the funny thing. In subgroup discovery, we don't care about everything. We only care about the subgroup. Like, hey, this group behaves strangely.
Yeah. Okay.
What the rest of the data does, maybe it's also strange, maybe differently strange. Maybe there's 20 strange subgroups, but we focus on this group is strange, that group is strange, this group is normal, so we don't report it.
Yeah.
So we give you, as the domain expert, number of the strangest groups.
Yeah.
And then typically we combine this, okay, you rather have a large group that is very strange than a very small group that is very strange, because then you're probably just looking for some weird exception, right? That
outlier,
So, but this is a line of research, subgroup discovery, that we explored quite extensively within material science, amongst which for this rock salt zinc blend setup, right, these octet binaries, we called nanoclusters for connectivity. They were interested in photovoltaics.
That's fascinating. Talking about subgroups of materials,
yes.
Do you have a favorite material?
That's a good question. That's a good question.
It's of course leading the question.
Yeah, well, so we already established I'm not a material scientist. I'm a computer scientist, and that's so. Hence, there's only one material that is truly close to my heart, which is sand. Which is sand. So, or specifically, silicon. Silicon, right? I mean, that's effectively computer chips, right? And that's are just sand, right? We just heated it up quite a bit, right? And we somehow through lithography we put it in the right structure. But in the end, right? I mean, what is really driving today's technology are computer chips. This is amazing, right? I mean, that's so this is why I grabbed my glass, of course, right? I mean, everything is connected. Sand is also fantastic if you want to have a sip of water, right?
Yeah.
And that's as a container. I mean, it's see-through, it's clear, it's beautiful. So I think silicon or sand, common sand, is my favorite material by far.
Yeah.
Even though I've never done material science-focused research on it, I use it every day in many, many forms.
And that's perfect, because you do use it a lot, and as we had at the start, just before we started the podcast, you were interested in tea, which is also, it's great for holding.
Exactly. Yeah.
So that's wonderful. So with these computer chips, with your AI models, your machine learning models, all these kind of things, you've discussed now for a while, all these possibilities and all of these potential of what you can do with them.
Yeah.
Where do you think this is going in the future? Let's say everything that you're visioning right now, right? Everything that you're imagining in your insane mind, or what you call your insane mind.
I'll happily take it.
If it comes true, let's say, what do you see in the future? Let's say 10 years, 20 years. I don't know when this would be, when this would come to fruition, but how do you see it panning out?
So where I would like to go, what has always been my goal, is to have really methods that can, or tools, right? We humans are tool builders that can really support scientific discovery. This is really the thing that I do believe in, right? So this is also why my first truth, I mean, e-science I didn't like for whatever reason. Right? I mean, if I now look back, it's exactly what I'm doing.
Yeah.
It doesn't make much sense, right? But really having tools that if you say, okay, well, for example, for drug discovery or for materials discovery, right? I mean, what makes this material floppy and this one have this property, right? That we have tools that can identify, hey, it's this or that or such or so, that can give you really clearly phrased hypotheses.
Yeah.
For which, like, hey, I say this because this is this evidence, right?
Yeah.
But this is then weird, right? I don't know how this works. So we need to do some experiment.
Yeah.
And then you can say, but wait a second, actually, this makes sense because such and so, right? So let's not do this. But this is blue laser type of thing. This is actually very special, and I can't really explain it. Let's dive a bit deeper, right?
Yeah.
And then figuring out, hey, wait a second, we have found now a new class of materials that behaves really differently, right? I mean, that's by taking this very simple, run-of-the-mill molecule, but applying this pressure to it, it behaves differently.
Yeah,
right?
yeah.
So really having an interplay between human scientists and, well, data-driven algorithms.
Yeah.
This is where I really want to be. And I really think that we're getting there much more quickly than I thought. And this is also where LLMs are, I think, beautiful. I mean, the real machinery, sort of like the reasoning machinery, there are a lot of groundwork to be done. But the beauty of LLMs is that rather than having the domain specialist having to learn how to speak algorithm, right, how to operate my algorithm, with LLMs, in natural language, we can interface. And that is beautiful.
That makes a huge difference.
And that is, I think, the biggest leap forward that we've seen from machine learning, that is interfacing. All of a sudden, normal people can use these tools. Well, to what extent and when should we use them and how can we trust them? These are all questions. But
that's with any scientific discipline.
Exactly.
But okay, so I think I will end it a little bit here. And I think my takeaway from this is that, by bringing like causality or understanding causality and reasoning into these AI models, we can basically usher in like a golden era of discovery in the sciences, at least, and probably in all other fields also.
Yeah, but I care a little bit less about those.
Yeah, sure. But I mean, as scientists, you and I think this is a beautiful vision to look ahead to. So this is an amazing conversation, Hiris. I was a little bit nervous going in, not knowing enough about the nuances of AI and machine learning and data science and so on. But you brought it out beautifully, and I enjoyed this conversation a lot. I'm sure everyone listening to the podcast also would have enjoyed it. Catch us on YouTube, on Spotify, on every other channel that we are on. We are also on Instagram, Blue Sky, LinkedIn, and so on. So see us all there, and catch you in the next podcast. See ya, next episode.